So for this lesson, we are talking about symmetry and even and odd functions. Those two do have a pretty tight relationship, so it's very easy to put them together. So you have two types of symmetry that you will see in functions. The first one that you will see is what is called line symmetry. And so this is a graph that can be folded along a line so that the two halves match. So this first example right here has x-axis symmetry because you can fold it along the x-axis. And then this function right here has y-axis symmetry because you can fold it in half along the y-axis. You also will see what is called point symmetry. And so this is a graph that remains unchanged when it is rotated 180 degrees around a point. So the common point that we use is the origin. So if you do turn your notes upside down, you will see that this graph has origin symmetry because you can turn it upside down at the origin and it be completely unchanged. So the x-axis and the y-axis are common lines of symmetry that we look at, and the origin is a common point of symmetry. So we do have tests for symmetry that we use quite regularly. And so for the x-axis, you can test it graphically by looking for every point that is xy on the graph. The point x negative y should also be there on the graph. The algebraic test is by replacing y with negative y and then simplify to see if it results in an equivalent equation. For y-axis symmetry, you can test this graphically by looking for every point xy on the graph. You should have a corresponding point of negative xy. You can also test this algebraically by replacing every x with a negative x, and it should result in an equivalent equation. For origin symmetry, for every point xy on your graph, you should have a point negative x and negative y that also exists on your graph. You can also test this algebraically by replacing y with negative y and x with a negative x, and you should get a similar equation. So let's go ahead and look at these functions and test their symmetry. So we will test for all three types. I do have the graph here that you can see, but I do want to test this algebraically. So for x-axis symmetry, you need to replace that y with a negative y. So for the x-axis test, we will get a negative y, and so that's x to the fourth minus 4x squared. And then if I try to get that negative y off, or that negative off the y, I have y equals negative x to the fourth plus 4x squared. That is not what I had in the beginning. So this one is a no. So x-axis does not exist. Then for y-axis symmetry, I will replace x with negative x. So we'll have y equals negative x to the fourth minus 4 times negative x squared. So negative x to the fourth is x to the fourth. And the negative x squared is x squared. So that is what I started out with. Then for origin symmetry, we've got to replace both. So let's see. Might have more room over here. So we'll have negative y equals negative x to the 4th power minus 4 times negative x squared. So first of all, these x's will simplify out. So we'll have x to the 4th minus 4x squared, but I still have the negative y. So I try to get rid of it. It sends me to negative x to the 4th plus 4x squared again, which is the same problem I had with x-axis symmetry. So origin also does not work. So the only one that does work is y-axis symmetry. So let's try with number 2. So I have for x-axis, I have to replace with a negative y. So if I have x times negative y equals 6, that's a negative xy equals 6. And I cannot get that negative off of it. So that one does not work. So if I try y-axis and I try negative x times y equals 6, that's again negative xy equals 6. That still does not work. And then for the origin, we have negative x times negative y equals 6. So we have xy equals 6. This works. So origin symmetry does work. So now let's try example 3. So this equation is a little bit longer, but it will be okay. So for x-axis symmetry, we will have 4 times x plus 3 squared plus negative y squared equals 16. That negative y squared will simplify out and we will have what we started with. Okay, so x-axis does work. Now for y-axis, we will have 4 times negative x plus 3 squared plus y squared equals 16. And so for this, we actually don't have a way to get rid of that square and get rid of the negative. So this one automatically just does not work. Now for origin symmetry, we have to replace both, but we're going to run into the same problem with the x's that we just had. The y will resolve. But to get rid of the negative on the x, you're actually going to flip the sign on the 3, which it's not going to work. So x-axis is the only one that exists there. So on our next function, let's go ahead and look at x-axis symmetry. So we're going to have negative y squared minus x squared equals 1. And that change to the y will resolve and become just y squared again. So we do have x-axis symmetry. Now I'm sure you're thinking by now, well, if we have one, we should be done. The rest of them won't exist. That's not always true. That is why we do have to test all 3. So for y-axis, we're going to do a negative x squared. And so y squared, and then negative x squared is x squared. So we're back to where we started. So y-axis does exist as well. So does origin exist? Let's see. So we would have negative y squared minus negative x squared equals 1. That leaves us with y squared minus x squared equals 1. Yes, this one exists too. So let's look at number 5. Number 5 might be a different situation. So let's see. We have for x-axis, we have a negative y equals the cube root of x minus 1. So to try to get rid of that negative y, then that just puts the negative back on the rest of the function. So that is not going to work. Let's try y-axis. So we have y equals the cube root of negative x minus 1. And so negative x minus 1, we've got really no way to get rid of it. So y-axis doesn't work either. Let's try origin. So that gives us negative y equals the cube root negative x minus 1. So we still have the same problem with the x. And if we try to get rid of the negative on the y instead, we end up with a negative cube root of negative x minus 1. And that doesn't work either. So this one actually has no symmetry whatsoever. So let's talk about even and odd functions. So this does relate to symmetry quite a bit. So this is why we put it together. But a function is even if it is symmetric with respect to the y-axis. The algebraic check for this is that if you plug in a negative x, just like the symmetry test, you get the f of x. So these tests are identical. But a function is odd if it is symmetric with respect to the origin. And the algebraic test for this is plugging in a negative x, and you get the negative f of x. So in even, you get the same function. And then with odd, all signs flip. Now you've already seen times where this doesn't always happen. So what happens when some of the signs flip and some of them don't? Well, that is when you have neither. So let's go ahead and look at testing for even, odd, or neither. So the test is always the same. You're going to plug in a negative x. So for number 6, we're going to have the f of negative x equals negative x cubed minus negative x. So that's going to give us negative x cubed plus x. And in this case, both signs flipped. So all signs changed. So our function is odd. Then for number 7, we have f of negative x equals the square root of negative x squared minus 4. So in this case, we have the square root of x squared minus 4. And so no signs changed. So this function is even. And so this function is symmetric. I forgot to do that on the last one. Over the y-axis. And this function is symmetric over the origin. Then for number 8, we're still going to plug in the negative x. And so that gets us a negative x plus 1. And then we can't go anywhere with this. So some signs changed. But not all. So this is neither.